Imagine you're floating in space. Ahead of you is a perfect circle of darkness. No explosions, no fire, no sound, just absolute black. It doesn't look dangerous, but hidden within that darkness is a boundary unlike anything else in the universe. Cross it, and according to Einstein, there is no way back. Not because something pulls you out, but because the very fabric of space and time has changed direction. This is the event horizon, the edge of a black hole. Today we'll explore what really happens there, why physicists believe time itself begins to behave differently, and whether anything, not even light, can escape once it crosses that invisible line. Black holes have earned a reputation as the universe's ultimate vacuum cleaners, cosmic monsters that swallow everything around them. But that's one of the biggest misconceptions in astronomy. A black hole doesn't roam through space pulling distant planets, stars, and galaxies into its grasp. In fact, if our sun were somehow replaced by a black hole with exactly the same mass, Earth wouldn't suddenly spiral inward. Our planet would continue orbiting almost exactly as it does today. From this distance, gravity would remain unchanged. So what makes a black hole so extraordinary? The answer isn't that it has more gravity than other objects of the same mass. It's that an enormous amount of matter has been compressed into an unimaginably tiny region of space. The closer you get, the more dramatically gravity intensifies, bending the very fabric of space-time. More than a century ago, Albert Einstein revealed that gravity isn't an invisible force pulling objects through empty space. Instead, mass reshapes space-time itself. Planets, moons, and even light simply follow the curves created by that distortion. Near a black hole, those curves become so steep that every possible path begins to lead inward. Even light, the fastest thing in the universe, can no longer find a route back out. Not because light slows down, but because space-time itself is collapsing inward faster than light can ever escape. At that point, the universe no longer offers a path outward, only a journey deeper into the darkness. Surprisingly, the event horizon isn't a physical barrier. There is no solid wall waiting for you. No glowing boundary, no invisible force field, no alarm that tells you you've gone too far. If you were falling into a sufficiently large black hole, you could cross the event horizon without feeling anything unusual. No sudden jolt, no flash of light, no change in the air, because there is no air at all, and that's exactly what makes it so unsettling. The event horizon is not an object, it's a limit. The point where escape stops being a possibility and becomes a violation of the laws of physics. Imagine standing beside a massive waterfall. Far upstream, the current is gentle. You can swim freely in any direction. As you drift closer, the water pulls harder. Every stroke requires more effort. Then you reach a critical point. Beyond it, the current becomes stronger than any swimmer could ever overcome. No matter how powerful you are, the river decides your fate. Surprisingly, the event horizon isn't a physical barrier. There is no solid wall waiting for you. No glowing boundary, no invisible force field, no alarm that tells you you've gone too far. A black hole works in much the same way, but the river isn't made of water. It's made of space-time itself. Beyond the event horizon, every possible path through the universe leads inward. Even if you fire your engines at full power, even if you travel at the speed of light, every future points toward the center. At the edge of a black hole, the geometry of the universe has fundamentally changed. There is no road back, only deeper into the unknown. Now, something even stranger begins to happen. Near a black hole, it isn't just gravity that changes. Time itself begins to behave in ways that seem impossible. Imagine watching an astronaut slowly drift toward the event horizon of a supermassive black hole. From your point of view, something extraordinary happens. Their clock begins to tick more slowly. Every movement becomes more sluggish than the last. Even the light reflecting from their spacesuit struggles to escape the black hole's immense gravity. As that light loses energy, its color gradually shifts toward deep red, a phenomenon known as gravitational redshift. The closer they get to the event horizon, the dimmer and redder they appear. Eventually, their movements become so slow that they seem completely frozen, forever suspended at the very edge of the black hole. To you, they never actually cross the event horizon. Instead, they simply fade away until they're no longer visible. But for the astronaut, reality is completely different. Their watch continues ticking normally. Their heartbeat remains steady. They don't feel time slowing down. There is no invisible wall, no sudden flash of light, no violent impact, no warning that they've crossed one of the most mysterious boundaries in the universe. They simply continue falling, unaware that, to the rest of the universe, they've almost stopped in time. This is one of Einstein's most astonishing predictions. Two observers witnessing the same event, yet experiencing two completely different realities. And remarkably, both are correct. Experiments have confirmed gravitational time dilation countless times. Even the GPS satellites orbiting Earth must constantly adjust their clocks because time passes slightly faster for them than it does on the planet's surface. Near a black hole, however, those tiny differences become so extreme that time itself appears to almost stand still. Whether you survive crossing a black hole's event horizon depends entirely on one thing: its size. A small stellar black hole is almost instantly fatal. Its gravity changes so dramatically over just a few meters that your feet are pulled far more strongly than your head. These extreme differences in gravity create immense tidal forces, stretching your body beyond anything matter can withstand. First, your bones begin to separate, then your muscles, then your cells. Eventually, even your atoms are pulled apart into an impossibly thin stream of matter. Physicists call this terrifying process spaghettification. But supermassive black holes are surprisingly different. At the center of our galaxy lies Sagittarius A Stur, containing more than 4 million times the mass of our Sun. Because it is so enormous, its gravitational pull changes much more gradually across your body. In theory, you could cross its event horizon without feeling anything unusual at all. The event horizon itself wouldn't destroy you. Instead, the true danger lies much deeper inside, where gravity becomes overwhelming and the known laws of physics begin to break down. At the very center of every black hole lies something that continues to challenge our deepest understanding of the universe. Physicists call it the singularity. According to Einstein's theory of general relativity, gravity never stops compressing matter. Every atom, every particle, and every fragment of energy is crushed into a region with no measurable size, creating a point of seemingly infinite density. As this collapse continues, space itself becomes infinitely curved. Distances lose their meaning. Time, as we understand it, appears to come to an end. But in physics, infinities are often a warning sign. They usually don't mean nature has become infinite. They suggest that our mathematical models have reached their limits. This is where two of humanity's greatest scientific achievements collide. General relativity describes gravity on the largest scales with astonishing precision. Quantum mechanics governs the strange behavior of the smallest particles in existence. General relativity and quantum mechanics have both been tested with extraordinary success. Yet inside a black hole, their predictions completely break down. Some physicists believe singularities never truly form. Others propose hidden quantum structures, or even entirely new regions of space-time. For now, the truth remains one of science's greatest mysteries. Black holes aren't simply places where gravity is strong. They're laboratories where the universe tests the limits of reality itself. At their edges, space changes direction. Time slows almost to a stop. Light loses its freedom, and the laws of physics begin to unravel. Every image we've captured, every gravitational wave we've detected, every equation we've solved, has revealed only the outermost layer of their mystery. Beyond the event horizon lies a universe forever hidden from us. Perhaps one day, a new theory of quantum gravity will finally reveal what truly happens inside. Until then, the edge of a black hole remains one of the last places in existence where human knowledge simply ends. Fade to black.